Welcome to The Explainer. We've all experienced that pure magic of typing a quick prompt into an AI and getting a brilliant essay back in seconds. But how does that actually happen? Well, today, we're doing a deep dive. We're getting into the highly technical, under-the-hood life cycle of a modern large language model. We are going to go step by step, from the microscopic interactions of single tokens, literally all the way to how it generates human-sounding text. So, let's just jump right in.
Okay, here's our roadmap for today. We're simulating the actual assembly line of these models. We'll be hitting the core attention mechanism, encoding position and context, breaking the memory bottleneck, scaling up with parallelism, post-training and human alignment, and finally, generating output via sampling.
Right, starting off with Section 1, the core attention mechanism.
At its absolute core, attention is really just a math trick. It's how the model decides which words in a sentence actually matter most to the exact word it's looking at right now. Without it, the model would just see a chaotic jumble of letters. Instead, it computes these weights that act like a spotlight. It basically turns up or turns down the influence of specific tokens. So, if the model is reading the word bank, that attention spotlight scans the surrounding text to figure out, wait, should I focus on river or should I focus on money? And that completely changes the mathematical context of the word.
Now, whether an encoder is filling in blanks or a decoder is autoregressively predicting the next word, the underlying math is exactly the same. The model calculates the sequence probability by chaining together the mathematical likelihood of each individual token based purely on the ones that came right before it. It essentially takes the probability of a whole sequence and breaks it down into a rigid step-by-step prediction.
Okay, so what is the mechanical sequence of how that attention is actually calculated? Well, it starts by projecting the input into three distinct vectors: a query, a key, and a value. You can think of the query as what a token is looking for, the key as what a token contains, and the value as the actual underlying information. We then calculate raw similarity scores using a dot product of the query and the key. But here's the absolutely crucial part. We mathematically scale these scores by dividing by the square root of the key dimension. Why? Well, if we don't do this, high dimensions create these massive dot products that push the subsequent softmax function into areas where the gradients are just tiny. And when gradients get tiny, the model literally stops updating its knowledge. The whole learning process just stalls out completely. Finally, we compute our context-aware representation by multiplying those normalized probabilities by the value vectors.
Moving right along to Section 2, encoding position and context. You see, unlike older models that kind of just blindly memorized fixed positions from scratch by adding a rigid independent vector to every single sequence slot, modern models do something much smarter. They use rotary position embeddings, or ROPE. ROPE actually bakes distance directly into the math by applying a geometric rotation to the data. Imagine all your tokens sitting on a clock face. The angle between any two tokens inherently represents how far apart they are. As that angle gets bigger, their mathematical similarity naturally decays. It's brilliant.
And to push these LLMs to process massive context windows, we're talking about reading an entire book in one go, researchers basically manipulate the scaling laws of ROPE. It acts like a multi-scale clock. The low dimensions rotate super fast, like the second hand on a clock, to track local grammar. Meanwhile, the high dimensions rotate really slowly to preserve broad themes. So instead of just stretching the entire clock and completely ruining the model's grasp of local grammar, they use techniques like NTK by parts interpolation. This mathematically leaves the fast-moving hands alone, preserving the local sentence logic, and only tweaks the slow-moving hours hand. That's exactly how these stretch the model's memory to millions of tokens.
All right, Section 3, breaking the memory bottleneck.
So, standard attention creates this intermediate n by n matrix, where n is the length of your sequence. And that means if you double the input text, you quadruple the memory you need. No way around it, that just eats up hardware bandwidth. This prompted a massive engineering pivot known as flash attention. The core insight here is actually pretty profound. What if we just never materialize the n by n matrix in memory at all?
Standard attention creates a massive traffic jam because it's constantly writing intermediate data to the GPU's high bandwidth memory, or HBM. That's the slower main memory. Flash attention bypasses this entirely. It keeps the computations inside the GPU's ultra-fast but much smaller SRAM. It reads the keys and values multiple times in discrete little blocks, so it completely avoids writing that massive attention matrix back and forth to main memory.
Think of it like reading a textbook. The key value cache is the book sitting on your shelf. It has to be there. The standard attention matrix is like writing down a giant pile of rough notes that you then have to sort through later. Flash attention basically says, look, instead of writing down all those rough notes and running out of desk space, just read the book page by page and write your final summary directly.
By stepping through the data in these discrete tiles, we bypass that global memory bottleneck entirely. The model loads blocks of query, key, and value into that super fast SRAM. It calculates the unnormalized scores locally and updates a really vital mathematical denominator called local sentence entropy. You can think of this denominator as a running tally. It keeps track of the total attention weights it's seen so far. That ensures that when the blocks are finally combined, the math is exactly identical to computing the whole massive matrix at once.
Up next, Section 4, Scaling Up with Parallelism. So, when models and context windows get so unbelievably huge that they just won't fit on a single chip, we have to slice up the workload. We do this using parallelism. Tensor parallelism divides the mechanical brains of the model, meaning it splits the individual attention heads across different GPUs. But sequence parallelism, that tackles ultra-long inputs by chopping up the actual text itself. It splits the tokens across devices, and then those devices communicate their partial results to each other to form the final coherent output. Using really clever techniques like ring attention, we set up an all-to-all communication network. Imagine 8 GPUs sitting in a circle, passing those local sentence entropy updates to their neighbor like a baton in a relay race. This continuous recursive loop lets them completely bypass single-chip memory ceilings, meaning they can process book-length sequences that would instantly crash a single chip.
Okay, Section 5, Post-Training and Human Alignment. How does a model transition from just a raw text predictor to an actually helpful assistant? Well, it goes through a rigorous assembly line of post-training. First up is base pre-training. This is where it churns through trillions of words to learn grammar, facts, and basic reasoning. Next is supervised fine-tuning, or SFT, which teaches it to actually follow instructions using highly curated prompt response pairs. After that, we collect preference data by having humans rank multiple responses. And finally, we use reinforcement learning to penalize bad behavior and align the model with human expectations. This is exactly what turns a wild, unpredictable text engine into that polite, helpful chatbot you probably use every day. Now, the classic method for this final step is called Proximal Policy Optimization, or PPO. But PPO requires a clunky, separate reward model to act as a referee, which frequently leads to mathematical instability and collapse. Direct Preference Optimization, or DPO, is a total game changer here because it completely eliminates the referee. Through mathematical inversion, DPO treats the human preference data as the reward directly within the model's own policy. This makes the training incredibly stable and way more resource efficient.
And finally, Section 6, Generating Output via Sampling. The model doesn't just confidently spit out a final word. It actually generates a list of raw, unnormalized scores called logits for every possible word in its entire vocabulary. Then, a softmax function converts these logits into actual probabilities that sum up to exactly 1.0. From there, we apply sampling filters. Top case sampling trims the list down to a strict fixed number of likely tokens. Or we can use top P, also known as nucleus sampling. This trims the list based on cumulative probability, meaning the pool of choices expands or shrinks dynamically based on how confident the model is right at that moment. But before we even sample, we apply temperature. By tweaking the temperature, we are literally scaling those logits before they hit the softmax function. At a really low temperature, like 0.2, the distribution sharpens up, heavily favoring the absolute most likely word. That is perfect for factual, highly predictable text. But at a high temperature, like 1.5, we flatten that distribution out. Suddenly, unlikely words get a fighting chance. This massively boosts the model's creativity, which is fantastic for writing poetry, but is exactly why the model might just confidently hallucinate complete nonsense when you ask it for hard facts. And that is the complete life cycle, from turning words into absolute numbers, applying rotational embeddings for position, processing them through memory-efficient flash attention blocks sliced across massive GPU clusters, refining that raw intelligence through reinforcement learning, and finally sampling the exact right word to show on your screen. It is an absolutely staggering feat of mathematical and engineering orchestration, and it's happening in fractions of a second for every single word generated.
Which leaves us with a massive open question about the future. As we continually hack our way to 1 million token contexts using advanced positional scaling and infinite ring attention loops, we are pushing silicon to its absolute physical limits. So, will hardware bandwidth eventually force us to abandon the attention mechanism entirely for a completely new architecture? Or is attention, optimally sharded and dynamically scaled, truly all we will ever need? Thank you so much for joining me on this deep dive in the explainer. Keep learning, and I'll catch you next time.